This is the first of probably two lectures on greedy algorithms. And in particular, today we'll be talking about greedy algorithms for scheduling problems. We'll go over three algorithms for three problems: interval scheduling, interval partitioning, and scheduling to minimize lateness. These are the same treatments essentially that are in the textbook. So greedy algorithms are a general class of algorithms that work as follows. They construct a solution in small steps, and at each step, they myopically make a choice that optimizes some simple property. So if you think about making a schedule, it means making individual choices about parts of that schedule. And each choice tries to do something well in a very simple notion of well, kind of hoping that in the end, all those simple choices will end up being leading to a globally good schedule. Okay. So an algorithm that we studied several lectures ago, the Gale-Shapley algorithm, is a kind of greedy algorithm. At each step, some hospital makes a proposal to their most preferred student that they haven't proposed to yet. So that's a greedy step. And the students, when the proposal's made to them, they simply say yes. That's a greedy step too. They don't think about what might happen in the future. Of course, they have the option of rejecting in the future, but the decision is a greedy one. Cashiers are taught to use a greedy algorithm for making change with the minimum number of coins. At least they used to, and nobody. It's several months since I saw somebody actually make change. We just tap plastic mostly these days. But if you need to give back change, you don't want to give back a lot of coins. You want to give back as few coins as possible, right? And so the algorithm for doing that is you choose as many quarters as possible without going over the amount you need to give. And then if you haven't reached the amount you need to give, you choose as many dimes as possible to get closer, and then as many nickels as possible to get closer without going over, and then finally as many pennies as are needed to get the exact amount that you want. Greedy algorithms are often very simple, often very efficient, and it's often not even hard to think of them. But finding ones that actually work is harder, and proving that they work is also sometimes easy, but often a fair amount of work. Okay, the first of our problems that we're going to consider is called interval scheduling. So an instance of the interval scheduling problem consists of a set of n jobs. So we'll call them jobs, but they can be requests or activities or any number of things depending on the actual application involved. Okay, and each job has a start time and a finish time. Okay, so there's an interval of time over which the job needs to be executed. Okay, we say two jobs I and j are compatible if their times don't overlap. That is, if one finishes before the other starts. And we say they conflict if their times do overlap. That is, if we take the interval for job I and the interval for j, and their intersection is non-empty, then there's a conflict. So they cannot be executed by a machine at the same time. Okay, the problem is to find a maximum size compatible subset of the input jobs, right? So a compatible subset is just one where no two jobs in that set conflict. And we'll call that an optimal set. Okay, so here's an instance with 5 intervals. And what's the maximal compatible subset? Well, these two conflict. These two conflict, so we can't take both of them. And these two conflict, so we can't take both of them. What can we take? Well, we can take this one, right? And if we take that one, we won't be able to take this one, but we could take this one. Okay, and if we take it, we won't be able to take either of these. So maybe that wasn't such a good choice. Let me back up. And instead, let me say, I'll take this one, and then I can take this one too. So then I get 3. Illustrated here. Okay, so what I did there is I took a guess, and then I saw that it wasn't so good and tried a different one, right? And that's not a greedy algorithm. So we're going to try to do something where we don't take guesses and then give them up. Okay, so the idea for a greedy algorithm for this problem and many problems is we're going to order the jobs according to some property of them. And then we'll repeat the following. We select the best job remaining. Okay, that will be the first one in the ordering. Okay, and then we reject all the jobs that conflict with it, right? And at the end, we output our set of selected jobs. So what should our property be? Let's think about a few candidates. Okay, so the easiest one might be pick the one that starts soonest. Okay. The minimum start time. Unfortunately, that's easy to see that often doesn't work. So here's an example where it doesn't work. If we pick the earliest start time in this example, we choose this one job, and these all conflict with us, so we can't do any of them. Okay, but obviously there's a much better solution. And the solution is to ignore the one that starts first, and then we get to pick all 4 of the other jobs. Okay, so what was wrong with choosing the earliest start time is we could pick the earliest start time could be a long job that makes it impossible to pick any other. So suppose we take shortest duration, take the job that burns up the least time, leaving lots of time for other things. Well, that works for this one, right? Take the shortest duration, it's this one. Okay, that eliminates this long one, but then we get to choose all the other 3. Unfortunately, it also fails for some fairly simple ones. It fails for this one, right? So that shortest duration says we would choose this, and then both of these would be ruled out, right? But obviously, so that's a solution of size 1, right? But obviously, we have the option of choosing these 2 instead, and that's preferable. Okay, so another option is to choose the job that remains that has the minimum number of conflicts. What does that mean? Well, in this picture, this job conflicts with 3 others, right? And this job conflicts with maybe 4 others, but this job only conflicts with 2 others. So we would choose it first. Okay. So unfortunately, it doesn't work. It does work for these previous ones. Okay, so if I do minimum conflicts, this one has 2 conflicts, so I wouldn't choose it, but I would choose one of these, eliminate this, and then choose the other. Or if I look at this one, minimum conflicts, any one of the, so the long job has 4 conflicts, but each of the others only has 1. So I would simply choose any one of the others. I eliminate the long one, but then I get to choose the 3 other short ones. Okay, but here, this is the minimum conflicts job. I have to choose it. Once I choose it, these 2 are eliminated, right? And then these all conflict. So I can choose at most one of these, and these all conflict. I can choose at most one of these. So I get 3. But with a different strategy, it's easy to see. I can get a solution with 4. Okay, so what works if none of those work? A slightly less intuitive one, earliest finish time. Okay, so we can describe the algorithm as follows. Start with A will be our accepted set of jobs. Start with it empty. And then as long as our collection of jobs is not empty, so there's still some we have to consider, let I be the job with the minimum finish time, early or earliest finish time. Okay. Add that job to our set of accepted jobs. And then from J, we'll delete all the jobs that conflict with I and I also. And once we've looked at all the jobs, there's no jobs left to consider, we output A. So what happens when we run that? An example, well, consider this example. Earliest finish time is what? It's this one. So we pick this one first. Now it gets a bit tedious to look at this. I'm going to do it a little bit different way. I'm going to lay these out differently. In particular, I'm going to lay them out in order of starting time. Okay, so then I get this picture. And now what will I do? I pick the job with the earliest start time. And then I have to eliminate any jobs that conflict with it. That's these two. And then among jobs remaining, I pick the job with the earliest finish. And then I have to reject any jobs that conflict with it, right? And I just repeat that. And that's my optimal solution. Okay, so we call an algorithm for an optimization problem optimal if it always produces an optimal solution. And this leads us to 2 questions. How can we tell that this algorithm is optimal? Assuming it is, we've claimed, kind of implied that it is. How can we tell that it is? And 2, is it efficient? How efficient is it? So let's rewrite the implementation to get an efficient implementation. What's the problem in here is you have to do this, find the job in J with a minimum finish time and delete all jobs that conflict. That seems like we have to do a bunch of operations on sets and some searching, but we don't have to do that. Okay, so here's a slightly different version. We'll order the jobs by finish time, as I did before. Set the set of accepted jobs to 0. And we'll keep a variable, we'll call it F, which will be the finish time, okay, of the last finish time of a job among those we've already selected. Okay, and then we'll run through the jobs in order. And if the job we're looking at starts after that last finish time, in other words, it doesn't conflict with any jobs we have already chosen, then we'll add that job to our set of accepted jobs and we'll update the finish time. All right, so how does that work? Let's just do a quick example. So we'll start with the finish time here. Okay, and we have the jobs ordered by non-decreasing finish time. So we'll start with the first one. Okay, and I'll accept the first one. Okay, because it starts after F, right? And then I update F to here. Okay, and now I consider the next job here. Okay, it starts before F, so I can't accept it. Okay, so I go to the next one. It starts before F, so I can't accept it. Okay, then I go to the next one. It starts after F, so I can accept it. And then I update F. And then I just continue, right? This is a reject. This is a reject. Okay, but this one I can accept. And when I do that, I update F to here. Then when I get to this one, it's a reject. When I get to this one, it's a reject. Right? When I get to this one, it's an accept. I update F, and then I just looks like I get that one too. Okay, so there's my schedule. What about running time? Well, theta of n log n to sort the intervals by finish time. All right, theta of n for the for loop. Right, pretty straightforward. Time is theta of n log n. Okay, what about correctness or optimality? So now I'll state the claim. Okay, the earliest finishing time greedy algorithm is optimal. We use various techniques for proving optimality of greedy algorithms. The one that's used here is sometimes called in the text, but greedy stays ahead. And what that means is that describes a situation where we show that as the greedy algorithm builds its solution, it's always doing at least as well as any other algorithm would in building a solution. And we'll see that actually happening next slide. So my proof is going to go like this. Suppose that A is the solution output by the algorithm, the schedule output by the algorithm, and let O be some optimal solution. Okay, I want to show that A is as good as O. So to reach a contradiction, I'll suppose that O is better than A. What does that mean? Well, the quality is just the size of the set, right? So that means M is larger than K. There's more intervals in O than in A. We will prove, okay, that the finish time of the ith job in schedule A is less than or equal to the finish time of the ith job in solution O. We'll do that on the next slide. So now we'll take that as a given. Okay. Then what happens? Well, if M is greater than K and this property holds, then our schedules look like this. A1 finishes before O1, A2 finishes before O2, right? The kth job in A, that's the last one, finishes before the kth job in O. And then there's some other jobs in O. We don't know how many, at least one. But this can't be, because these jobs here, in particular, this job is compatible with AK, right? I mean, it starts after OK ends, and OK ends after AK ends, so it's compatible. So actually, the algorithm would have included this interval. Okay, some number of intervals in there. Okay, so provided I can prove this property, we have that the solution A output by the algorithm is optimal. Okay, how will we prove that? So our lemma is, if A is the output of the greedy algorithm and O is some optimal solution, I'm going to show that the finish time of the ith job in A is at most the finish time of the ith job in O. We'll do it by induction on oops, little slip there. I, the job. Okay, so base case is I is 1. Okay, so the first job we put in A is the job actually with the smallest finish time. Okay, so the finish time of A, 1 is smaller than any other finish time and therefore no larger than the finish time of the first job in O. Our inductive hypothesis is consider some I greater than 1 and assume that the finish time of the I minus first job in A is no later than the finish time of the I minus first job in O. Right? And now we want to prove that the finish time of the ith job in A is no greater than the finish time of the ith job in O. Suppose the contrary, okay, that the ith job in A finishes after. Then we have a picture that looks like this. Here's the schedule A. There's the I minus first job ending. Schedule O, the I minus first job ending no earlier, right, than the one in A. And then we have the ith job in O, and the ith job in A is finishing later. Okay, so we have what? That the finish time of the I minus first job in O, this one, is at most the start time of the ith job. That has to be. And we have that the finish time of the I minus first job in A is at most the finish time of the I minus first job in O. That's the inductive hypothesis, right? So this one, okay, so we have that this one comes before here, and this one comes before here. Okay, so you put them together, and we have what? At the time that AI was chosen, OI was compatible with the jobs that were already in A, okay? But the finish time of OI is less than the finish time of AI. So the algorithm wouldn't have chosen AI at all, it would have chosen OI, right? Which has the earlier finish time and is compatible. Okay, so that's a contradiction, and we get our property. Okay, our second problem is a variation. So an instance looks the same. We have a set of jobs, and we have start and finish times for each job. Okay, but the setting is a little bit different. Here, we have multiple machines, right? It can be machines or servers or rooms, classrooms, meeting rooms, whatever, production lines. Depends on the application, of course. We'll just call them machines that can execute jobs. And we have to assign each job to a machine. Every job, right? Every job has to be assigned to a machine. The jobs assigned to, multiple jobs could be assigned to a machine, but if we have two jobs assigned to one machine, those jobs have to be compatible, right? They don't intersect. And our problem is we want to schedule all the jobs using the minimum number of machines. Okay, so an assignment of jobs to machines is the same as a partition of the intervals. So it's, right, that's where the interval partitioning comes from. And that's the same as coloring the jobs, giving the jobs colors, right, so that no two conflicting jobs have the same color. Okay, so here's an instance. And let me just go through it. So let's give this job to the blue machine. And this job is not compatible with it, so we can't give it to the blue machine, but we can give this job to the blue machine. Right? And then let's give this job to a different machine, the red one. And this job is not compatible with it, but this job is, so we can give that to the red one. And then we need one more machine to assign this job. And you can see, so that's a solution with 3 machines, but you can see actually the 3 machines are needed. Why? Because we have 3 jobs all overlapping, all intersecting at one point. So at that point, they all have to be assigned to different machines. And that's actually a property that we're going to use. So let's say for a set of intervals, the depth of the set of intervals is the maximum over all times t of the number of intervals containing t. Okay. So we claim if S is a set of intervals, every schedule for S has at least depth of S machines. And that's just really the argument I just made on the previous slide, right? If D is the depth of S, okay, then there's some time t when we have D different intervals, right, all hitting that time t. Each of them has to be assigned a different machine, so you need D different machines. Okay, so that leads us to 2 questions. Is the depth of S machines always sufficient, or do you sometimes need even more? And this doesn't seem to be quite obvious. And the second, of course, is there an efficient algorithm to construct an optimal schedule, a schedule using the minimum number of machines? Okay, and we're going to essentially answer these 2 questions at the same time by giving an algorithm and showing that it's optimal. Okay, so here's our algorithm. We input is our set of intervals. We're going to sort the intervals by non-decreasing start time. That is, so that if I is less than j, the start time of job I is no greater than the start time of job j. Let D be the depth of I. Okay, and I'm going to define a sequence of sets, Ci, one for each job, which is the set of j less than I, such that f of j, finish time of j, is at least the start time of I. What does that mean? This is the set of jobs that start before I does, but whose finish is after I starts. In other words, they're the jobs that come before I in the ordering, but that intersect with I. They're the jobs that are going to be given colors before I get to I. So they're the ones that use up colors I don't have available to use for I, right? Those are excluded colors. Okay, so then I'm going to go through the jobs in order for I from 1 to n. Let xi be what? The labels of the intervals in Ci. That means the colors that I don't have available to color the ith element, right? So then all I do is I label I, job I, or color job I, with something that's not in that excluded set. And then when I'm done, I open the set of labels. Okay, now the question arises, of course, can I always do this? Maybe sometimes there's no free color, free machine to assign to the ith element, right? But assuming it is the case, assuming I can always execute that line, then the algorithm labels every interval in I. Okay, and So then we have to show that this star is always possible, and that after we've done that, the intersecting intervals have different labels. And if we can show those two things, optimality follows by the choice of D, right? D is the depth of I, and that's the minimum possible number of labels or machines. Okay, so let's do a quick example. So I've ordered jobs by start time, and I'm going to go through them in order. And I just take the first one and I color it. So I'll color the first one. Okay. And then when I get to the second one, what do? I have to color it, give it a color that is some available color other than one that's overlapping it, right? So I'll color it red. Okay. When I get to the third one, then red is it's not really red, but that pink color, deep pink, is not available, but the blue is available again. So I'll color it blue. Okay. When I get to the fourth one, the blue and the pink are not available, so I need another color, right? And when I get to the fifth one, then I can't use the blue, but I could use the pink or the orangey color, either one. Okay, so there's a solution with 3 colors. And we know already this instance has depth 3. Well, you can see right here, depth 3. So that's optimal. Okay, so we need to prove this property. So for that one, consider an interval I. Okay, and suppose that Ci is T. What is Ci? Ci is the jobs that already started and overlap with job I, right? Okay, if we take Ci together with job I, that's a set of T plus 1 intervals, and all those intervals contain the point start of I. Okay, so what do we know? We know T plus 1 is no greater than the depth of the instance. Okay, and therefore T is less than or equal to D minus 1. And what does that tell us? That tells us the collection, the set of colors that we're not allowed to use when we need to assign a color to job I is strictly less than D. So there's always a color free. The step with the red asterisk is always possible. There's always a color available to use. Okay, and the proof of the second goes like this. Suppose 2 intervals I and j intersect, and that I is the one that comes first. Right? Then it must mean that I is in the set Cj. Right? That's how we defined it. The jobs that start earlier but intersect, right? Okay, so the label of I is in the set xi, and the algorithm chooses a label that's not in xi, follows that I and j have different labels. Okay. So this method of proving optimality, we call greedy meets a structural bound, right? The structural bound is we know by a basic structural argument that we need at least depth of D machines. And we've shown that the greedy algorithm always finds a schedule with only depth of J machines. Okay, so the greedy algorithm meets this structural bound. Okay, finally, we claim without proof that the greedy interval partitioning algorithm can be done in time big O of n log n. So this doesn't seem to be completely obvious. Why? So we have to do a couple of things. The sorting is n log n, of course. That's easy, right? You have to compute the depth of I. That seems to take a little thought. And then we have to keep finding these sets of labels that are currently not available. We have to keep updating those. So this can be done in time n log n, but it takes a little bit of work. And I'm leaving that as an exercise. All right, our third problem is called scheduling to minimize lateness. So here an instance is a little bit different. It's closely related to the first problem, but it's a little bit different. So we have n jobs, but instead of having each job having a fixed interval when it must be executed, we have a duration, how long it takes to do, and we have a deadline. So we can do it, we can choose to do it at different times, but we want it to finish before some deadline. We have one machine that can work on one job at a time, and we want to schedule all the jobs. So what does it mean to schedule a job? To schedule a job means assign a start time. So we need to assign start times for all the jobs. Finish times, of course, are fixed. So the start time plus the duration. And we want no jobs to conflict. That is, if we take two jobs, I and j, and the intervals during which they actually get executed, which are chosen by the algorithm, their intersection is empty. Now here, it's a little difference between the version, the first one. I've used open intervals, and using open intervals means we can have one job start at the same time that a previous one finishes. Okay, it's just a little bit more convenient for this particular problem to formulate it that way. Okay. We say a job is late if its finish time is after its deadline. And the lateness of a job is the maximum of 0 and the difference between its finish time and deadline. In other words, if it finishes before its deadline, its lateness is 0, and if it finishes after its deadline, its lateness is the amount after its deadline it finished. The maximum lateness of a schedule is, of course, just the maximum over all the intervals in a schedule of the lateness of those intervals. And now our problem is to find a schedule with the minimum maximum lateness. In other words, find among all schedules the schedule where the latest job is the least late, right? Or the best schedule where the quality of the schedule is determined by the latest job. Okay, so a little example. So here's, we have these are durations, the duration of job 1, the duration of job 2, the duration of job 3, and deadlines. Here's my deadline for job 1, my deadline for job 2, and my deadline for job 3. And I can schedule this as follows. The deadline for job 3 is very early, right? If I don't want it to be late, I have to put job 3 first. So let me do that. So this is job 3 here. Okay. And the deadline for job 1 kind of comes next. And so to make it not late, I have to put job 1 next. So I'll do that. And then job 2 comes at the end. And job 2 has this very late deadline, so it's okay. So this is a solution with 0 lateness. Now, suppose that the deadline for 2 was a little bit earlier. Right? In this same solution, 3, 1, 2, this is the lateness of job 2, right? It finishes a little bit after its deadline. And this seems to be an optimal solution, even though there's one job is late, because this job, if I were to reorder them so that this job was last, it would be really late. Right? And if I were to reorder them so that the second job was last, job 1 was last, it would also be pretty late. Okay, so this seems to be this seems to be the best I can do in this case. Okay, so here's our algorithm. We're going to order the jobs by non-decreasing deadline. Okay, so deadline. That's kind of just what I did in the previous slide, but we're going to show that that's actually the correct thing to do. Okay. And we'll keep track of the finish time of the last job that we've scheduled so far. Okay, and we go through the jobs one by one, and then we simply assign the start time for job I to be F, the finish time of the last job we scheduled. What does that mean? Job I goes right after job I minus 1. Okay, and then we update the finish time. We update F, which keeps track of how much time we've used essentially. Okay, and then our output is the set of intervals consisting of each start time. And for finish times, we just take the start time and add the duration. Okay, or we could express this more concisely as follows. Order the jobs by deadline, and then let the start time for the ith job simply be the sum of the durations of all jobs that come before I in the order. That's it. Okay, our running time is n log n. Why? We just have to sort them and stack them up, right? So the question now is, how can we show it's optimal? And this one turns out to be a little bit more work than the previous ones. So what we're going to do is we'll let A be the output of the algorithm. And then we want to show that A is optimal. And we'll do so very kind of roughly, not exactly, but we're going to imagine starting with some optimal schedule. And then we're going to transform that optimal schedule into A by making a bunch of small changes which don't increase its lateness. Okay. And the method here is called proving optimality by an exchange argument. The exchange is we're going to move some things around, right? These steps, we're going to move some things around in the schedule, right? To gradually turn O into A or into something close enough to A. Okay, first we need to establish some terms and a bunch of facts about schedules to work with. So idle time is time when a machine is not in use, but there's still work to do. Okay, so time when no job is scheduled, but there's some job scheduled for later. Our solution A, by construction, has no idle time, right? Each job starts right when the one before it finishes. Fact 1 that we're going to use, there's an optimal schedule with no idle time. How do I know? Well, it's pretty simple. Suppose this is an optimal schedule, and it has some idle time here. Well, we can just remove the idle time by just moving these jobs after the idle time up. Now what happens? Well, the lateness cannot have increased, right? These jobs didn't change. They have the same lateness as before. And these jobs moved earlier. So if their lateness changes, it must decrease, not increase. Okay, second term is an inversion. So we say we have an inversion if there's two jobs, I and J, and I starts before J does, but its deadline is after. Okay. Our solution A has no inversions by construction. Why? Because we added the jobs exactly in the order of their deadlines. Okay, so the job that's ith in the order by deadline comes ith in the schedule. Fact 2, all schedules that have no inversions and no idle time have the same maximum lateness. Okay, so this seems to me not obvious at all, but it's true. Consider two schedules, B and C. If those schedules have no inversions, What does that mean? That means the jobs are ordered by non-decreasing deadline. That's exactly what it means to have an inversion, is that you're not ordered by non-decreasing deadline. Right? If they have no inversions, and in addition, all the deadlines were distinct, what would that mean? That would mean the order of the jobs is completely determined, right, by their deadlines. So B and C would order the same jobs identically. And so the only way then B and C could be different is if they have some idle time. So if we have no inversions, all distinct deadlines, and no idle time, what does that tell you? It tells you B and C are the same. Okay, now we're only talking here about schedules with no inversions and no idle time. So how can they be different? B and C can be different only in the order of some jobs that have the same deadline. If you consider all the jobs with a particular deadline, they're all scheduled one after another, right? Not with no other jobs in between. They're scheduled after jobs that have earlier deadlines and before any jobs that have later deadlines. And if you consider all the jobs with some particular deadline D, the last one to be scheduled has the greatest lateness. And it doesn't depend on the order of them. If I swap the order of some of those jobs with the same deadline, still the last one has the greatest lateness, and that lateness doesn't change. Okay? It follows now B and C have the same maximum lateness. Okay. Fact 3. If a schedule has an inversion, it has two consecutive jobs that are in inversion. Just think about this way. So here's my schedule. Okay, and I have a job A and later job B. And I'm writing these bars to indicate their deadline, right? So this is A's deadline, and B's deadline is smaller, earlier, even though B comes after A in the order. So the claim is somewhere in here, there's a pair that's in inversion that are right next to each other. Just suppose, how do we see it? Suppose these B and the one before it are not such a pair, right? And suppose A and the one after it are not such a pair. That means this deadline is later than A's and this one is earlier than B's. Okay, now what happens in here? Well, if this one has an earlier deadline than this one, then there's an inversion between these two. And if it has a later deadline than this one, there's an inversion between these two. Okay, this is a special case of a very general property whose name escapes me at the moment. But now what we're going to do is we're going to take the fact that if there's an inversion, there's a consecutive inversion, and I'm going to get rid of that inversion. All right, so let B be a schedule, okay, where I and J are a consecutive inverted pair, and I'm going to swap I and J, okay, and claim that the resulting schedule, okay, has one less inversion. So here's B, C is the result of doing the swap. Here's I and J, and I swap them. Let me change the colors. I and J, and I swap them. Their orders like this, okay. So now I want to say, so I've eliminated one inversion, right? There used to be an inversion because of these deadlines, I and J, using the same scheme for indicating deadlines as last time. Okay, so I've removed that inversion. And what about other inversions? Well, suppose there's an inversion between some earlier job, let me switch colors, some earlier job and one of these. Well, what would it be? This one, okay? If there is, that was already an inversion before I did the swap. And similarly here, if there's an inversion between here and here, well, it was already an inversion back here before I did the swap. So I've reduced the number of inversions by 1 by doing that swap. Okay, fact 5, now we start getting into the nitty-gritty. The same setup, okay, we have a schedule that has some inversions. Okay, in particular, it has ij or a consecutive inverted pair, and I'm going to swap I and j to get rid of it. And I want to see that when I do that, I don't increase the maximum lateness. This is the key to the whole thing. Right? Okay, so what's going on here? Here's my schedules, B and C. Okay, and I have my job I and job J, and I swap them. Okay, and I've marked on here deadlines. Now, I don't know where these deadlines are really, but the interesting case is when the jobs are late, because I want to show that the lateness doesn't get worse. Right? And I do know that the deadline for J comes before the deadline for I, because J is after I in the schedule, and it's an inversion, right? Okay. I'm going to write below, I'm going to write, use some notation. So this is the start time of job I in schedule B. Should use the pointer. Start time of job I in schedule B. Finish time of job I in schedule B. And lateness of job I in schedule B. Okay. Job J moves earlier, so it cannot be more late after it moves earlier, right? Let's just set up for the next one. What I'm talking about is illustrated with these pink lines. This is job J, and this is how late job J is. I'm going to switch colors. This is how late job J is, right? And after we swap it, we move it up, okay? We move it up here, and now it's only this late. Okay, so it got better. And we can do that formally, right? The lateness of job J in schedule C is what? It's the finish time of job J in schedule C less the deadline of J. And that's less than the finish time of job J in schedule B minus the deadline for J. Why? Because the finish time in C is less than the finish time in B, because I moved it up, right? And that's just the lateness of job J in B, okay? So that lateness got reduced. What about job I? Now, job I is a bit trickier. Okay, because job I moves later, and therefore its lateness will increase. But it doesn't matter. It's sufficient that its lateness in C is not greater than the lateness that job J had in C, the other job. We don't care about the lateness of individual jobs. We only care about the worst one, right? Okay, so what are we looking at? Let's look at the green lines here, if we're not too messy already. Okay, so we're looking at the lateness of job I in schedule C. That's this, right? And now job I ends here. Okay. And this is the lateness of job J in schedule B. And we can see it's greater. Why? Because the deadline for J comes before the deadline for I. So that's what we're going to show formally. The lateness of job I in schedule C is the finish time of job I in schedule C minus the deadline of job I. And that's the same as the finish time of job J in schedule B, right? Minus the deadline for I. And that's less than the finish time of job J in schedule B minus the deadline for job J. Why? Because deadline for J is less than the deadline for I, and that's just the lateness of job J in schedule B, right? And so there's a less than there, okay? So we haven't made the lateness greater, right? Among these two jobs, whichever one is most late, that lateness didn't increase. Okay, so all the other jobs, of course, were unchanged. So I claim the max lateness of the schedule didn't increase. Okay, so now we're ready to wrap things up. Main lemma, there's an optimal schedule with no inversions and no idle time. How do we see that? Let B be an optimal schedule with no idle time. We know there is one, that's fact 1. And suppose that B has k inverted pairs. What we're going to do is we're going to modify B k times, each time by swapping a consecutive inverted pair. And after we've done that, we get a schedule that has no idle time, no inversions, and is optimal. So in there implicitly is an inductive argument, induction on K, where K times we apply facts 3, 4, and 5, right? To show, right, K times we can pick a consecutive inverted pair, swap them, right? And we maintain optimality, reduce the number of inversions, maintain having no idle time. Okay, and now we're ready to finish. Theorem, the schedule A produced by the earliest deadline first algorithm is optimal. Why? First, A has no idle time and no inversions. That's by construction. Second, there's an optimal schedule O that has no inversions and no idle time. That's by our big lemma above. Third, all the schedules with no idle time and no inversions have the same maximum lateness. That's fact 2. Okay, so it follows A and O have the same maximum lateness, so A is optimal. Okay, so we'll just briefly, to wrap this lecture up, review these techniques for showing greedy algorithms are optimal, right? Greedy algorithm stays ahead as it builds its solution. It's as good as any other. We use that for interval scheduling. The structural bound we used for interval partitioning. That is, we showed that the greedy algorithm always produced a solution that was as good as the best possible solution as shown by a structural bound on the problem instance. Okay, and an exchange argument, which we used to minimizing lateness to transform an optimal solution into one just like the one the greedy algorithm finds. That's it for this one.